Percent yield. Welcome to this short lesson on percent yield. Now, when a chemist carries out a reaction, he or she would like to know that it is as efficient as possible. There may be more than one way to obtain a particular product, so the chemist would like to calculate the percent yield to determine which is a better method. So, for example, suppose a chemist calculates that the maximum product that can be obtained is 250 grams. The reaction is carried out, the product is obtained, and indeed 250 grams is obtained. In that case, that would be a 100% yield. This is a very rare occurrence. There are always some losses due to the experiment, not necessarily carelessness, but inevitable losses that you can't do anything about. There may be competing reactions going on which diminish the amount of product. In the case of organic reactions, for example, sometimes a 5 to 8% yield is the best that you can hope to get. In inorganic reactions, often an 80 to 90% yield is possible. That's a good yield for inorganic reactions. Now, the percent yield calculation often follows a question on stoichiometry. So the actual formula is shown here. It's actual yield over theoretical yield. So the first thing we'll do is just get a handle on the meanings of these two terms. The actual yield is the actual amount of product obtained in the experiment. Now, this must be given in the question. Unless, of course, you do the experiment yourself, you can then obtain the product and measure it or weigh it, and that would be your actual yield. But in almost every case, you will be given the actual yield in the question. Now, the theoretical yield is the maximum amount of product that can be obtained theoretically. And this is done by calculation using stoichiometry. So you have to know how to do stoichiometry. If you're not sure or need to be refreshed on it, you should go back and do that, because we're going to apply the stoichiometry principles here. So let me repeat the percent yield formula here just for reference, and here is a typical problem. If 8.76 grams of lead fluoride solid precipitate is obtained when 4.5 grams of potassium fluoride aqueous is added to a solution of lead nitrate aqueous, what is the percent yield? So the first thing we should do is write a balanced equation, and you'll notice that I've got in black here, these are the substances of interest, whereas the brown is not are not substances of interest, so we'll just don't have to worry about them, but we have to have a balanced equation. So the first thing to do is put onto the equation the information that we see in the question. So I put the 4.5 grams here from KF up here, and then the 8.76 grams is the actual. Now, let's look at this word obtained. This is key. Now, how is this obtained? Well, it's done by experiment, and therefore it will be the actual yield. We'll then put X here for the theoretical, so that refers to the theoretical in the formula here. Once we get the theoretical, we can then use these two numbers to obtain the percent yield. It's also always a good idea to put the molar mass under the substance of interest, because we're going to be using them in our calculations. Notice that I didn't multiply this 58 by 2, because molar mass, as the name suggests, is the mass of 1 mole. This too will be used later on in our stoichiometry calculation. So also here then we'll put the molar mass of lead fluoride. So now we're ready to do our calculation using stoichiometry to find the theoretical yield. Let's start over on the left and show the relationship between moles and mass. N equals mass over molar mass. Let's put in our numbers, and our number of moles for potassium fluoride, 0.0776 moles. The second step involves the mole ratio between lead fluoride and potassium fluoride. So if we look up here, we can see we have 1 understood here, and there's 2 moles there. So it's always best to put the unknown on top. That makes the math easier. So the ratio between lead fluoride and potassium fluoride, as shown from the stoichiometry, is 1 to 2. So there we are. And it's easy enough now to find the rearrange to get lead fluoride by itself. That gives us 1/2 times the moles of potassium fluoride, and put in our numbers here, and gives us 0.0388 moles of potassium fluoride. Now we're ready for the third and final step. We go back to this equation here and manipulate it to get mass by itself. So N times molar mass of lead fluoride, put in our numbers, calculate 9.506. Remember, always show your units here, and in addition, make sure you identify what substance it is that you've calculated. So now we have our actual and theoretical. We're ready to apply the percent yield formula. Put in our actual yield over theoretical yield. We get 92.2%, a very good yield for this reaction. So this allows you to calculate the percent yield for any reaction that you're going to be presented with.